Hi. So in this video, I'm going to show you how we can apply the exponential function to model real-life scenarios. So in example 1, we're told that the concentration of a pollutant, C, is given as this model here, where T is the time in days and C is in micrograms per litre. We've been asked to use this model to estimate the concentration of a pollutant after 20 days. So with questions like this, I find it really helpful to sketch a graph of this model. We know that the time will start at 0, so it won't be negative, and that when time equals 0, this power, negative 0.005t, becomes 0. So this becomes 200 times 1. So 200 is our initial concentration. And as t increases, or tends to infinity, then we get C, it's going to be 200. Because this is a negative power, I'll write it as a division of e to the 0.005t. So this becomes 200 divided by a very large number. So as t tends to infinity, c tends to 0. And this is where we get the asymptote here. So you can see that this is a decreasing function. Okay, so for part A, estimate the concentration of a pollutant after 20 days. So we need to substitute in that t equals 20. So we've substituted 20 into our model. Then we can work this out on our calculators. So the concentration will be 180.97 micrograms per litre after the 20 days. For part B, interpret the meaning of a value 200 in this model. Well, we've said here that when t equals 0, the concentration is 200. So the way we interpret this is that the 200 micrograms per litre is the initial concentration of a pollutant. And then for part C, show that dc by dt is equal to kc, where k is a constant and we need to find its value. So we need to differentiate this with respect to t. So to differentiate this, we're going to need to use the chain rule. So if I introduce this third variable w and say it's equal to negative 0.005t, then our model becomes c is 200 times e to the w. So now we can work out dc by dt. Using the chain rule, this will be dc by dw multiplied by dw by dt. We know e to the w will differentiate onto itself, and this will become 200 e to the w multiplied by dw by dt, and when we differentiate this with respect to t, we get negative 0.005. So I'll substitute this into here. So now we can work out dc by dt. We'll multiply the 200 by this, and then we'll substitute the w back in terms of t. So dc by dt will be negative e to the power of negative 0.005t. So k is equal to negative 1 over 200. And then for part D, interpret the significance of the sign of your answer. So in this negative, but this tells us that the function is decreasing, which we can see from the graph. Okay, let's try one more question. Okay, so in example 2, we're told that a pot is placed in a cooled room, and as it cools, its temperature, t minutes after it's placed in a room, is given by this model, where t is greater than or equal to 0. For part A, we've been asked to find the temperature of a pot when it's first placed in a room. So again, I'm going to sketch a graph to model this. We know the initial temperature, which will be this value of theta here, will be when t equals 0. So if we substitute t equals 0 into our model, we get e to the power of 0, which is 1, multiplied by 350 plus the 20. So we'll get an initial temperature of 370 degrees C. And I can label this on the graph as our intercept. Now this horizontal asymptote is caused by this addition of positive 20. It was at 0, it's being translated 20 units up. So the cooling temperature will be at 20 degrees. We haven't been asked for this, but I find it really helpful to include on our diagram. We know it's a decreasing function because the temperature is cooling. Okay, so for part B, find out how long the temperature has been in the room before its temperature drops to 100 degrees. So now we need to set theta equals 100. We'll substitute this into our model, and then we'll solve the equation for t. We'll move this addition of 20 to the left-hand side, and then we'll divide both sides by the 350. So now we need to cancel out this e, so we'll take the natural log of both sides, and then these two will cancel. So the natural log of 8 over 35 will be negative 0.04t. And now we'll divide both sides by this decimal, and we'll get t is 36.89, which I'll round to 37 minutes. Okay? And then for part C, find the rate at which the temperature of a pot is decreasing when t equals 40. So we need to differentiate theta with respect to t. But again, we need to use the chain rule because of this power. So if we let u equal negative 0.04t, then we can write theta as 350 e to the u plus 20. We know d theta by du. This will differentiate onto itself, and this constant will go. So we'll get 350 e to the u. And du by dt, when we differentiate this, will give us negative 0.04. So d theta by dt will be d theta by du multiplied by du dt. We'll substitute each of these into here, and we'll write u in terms of t. The 350 multiplied by the negative 0.04 will give us negative 14, and then we'll substitute in t equals 40. We can work this out on a calculator, and we get a rate of negative 2.83 degrees C per minute. Okay? Well, thank you very much for watching. I hope you found that useful. If you did find that helpful, please like and subscribe, and you can download the full lesson from my website, mrmathematics.com. I'll leave a link in the description below.